Now we shall have a talk by Valentin Benedetti, who will speak about generalized symmetries and Noether currents. He's working at the Atomic Center of Bariloche. So please begin, Valentin.
Hey, hello, everyone. First of all, I would like to thank the organizers for the opportunity of speaking here and organizing this nice conference. I wanted to tell you today about some recent work we did in collaboration with Horacio Cassini and Javier Magan, mainly based on two papers of last year and one paper that is to appear probably this week on the archive. The main question I have been trying to understand for this couple of years is, when is there a well-defined Noether current for a continuous symmetry in quantum field theory? A priori, a Noether theorem asserts the existence of a local conserved current when the action is invariant under a continuous symmetry group. However, a long-standing question in quantum field theory is to determine to what extent or under what conditions Noether's theorems actually holds. The issue becomes a little bit more clear when one considers some counterexamples to Noether theorem. These are examples in which the Noether current is not gauge invariant. For instance, it's a case of the duality symmetry in the free Maxwell theory, or the Weinberg-Witten theorem that, for example, precludes the existence of the graviton stress energy tensor, and the chiral symmetry in quantum electrodynamics, massless, in the presence of the ABJ anomaly. What we want to understand is what is peculiar about the symmetry in all these cases, and how is the symmetry implemented in the absence of the current. The best setup, we think, to ask this question is the one of algebraic quantum field theory, in which we assign to a spacetime region R a von Neumann algebra of observables. Von Neumann algebra entails that the double commutant of the algebra recovers the original algebra. And quantum field theory imposes some minimal sets of requirements over these algebras. The first one is isotonity, which entails that if we have a region R1 that is contained in a region R2, then the algebra of the region R1 must be contained in the algebra of the region R2. And the second one is causality, which implies that the algebra associated to any given region must be contained inside the commutant of the algebra of the complementary region. These are not all the properties one can ask to a choice of algebras. The maximal sets of requirements includes isotonity, but also Haag duality, which is the saturation of causality, and additivity, which implies that the algebra generated by the algebra of two regions is the same as the algebra of the union of the regions. It has been seen that, yes?
Can I ask you a question?
Yes, sure.
It's about the first statement. You want to study the quantum version of the Noether theorems of the conservation of the current, right? Is this the word identities?
Well, in some cases it is related, and some problems might come from the word identities, but it also can happen in free theories. Like in the case of the duality symmetry in free Maxwell theory, you don't have to look at any word identity to see that you have a symmetry, but it's not implemented by a current.
Okay, thank you.
Okay, so when Haag duality and additivity are both satisfied at the same time for a given algebra assigned to some region, the assignation of the algebra to such region is unique, and the reverse statement also holds. During this talk, I will assume that all the algebras that can be associated to topologically trivial regions, for example, balls, satisfy all these properties, and their algebra is unique. The only known counterexample to this is the case of generalized free field, where this non-validity of Haag duality is clear from an holographic standpoint, but I will not talk about this today. I would like to focus in ambiguities that appear in quantum field theory for algebra assignations for topologically non-trivial regions. and these appear in the case of theories with generalized symmetries. More precisely, algebra ambiguities for regions with non-trivial homotopy group pi p appear in theories with p-form symmetries, namely theories that have observable formed fields that are p+1 forms that are close but not exact. These close but not exact statements might seem to at first contradict the Poincaré lemma, but the Poincaré lemma is exactly why it works. For instance, if we have a closed form field F that is a p+1 form, the Poincaré lemma states that F is the exterior derivative of a P form A, but this P form A it might have ambiguities in the sense that it's ambiguous by adding another exterior derivative. Indeed, what happens is that this field A may not be a physical operator in the theory. For instance, it might have a gauge symmetry, and it's not an observable that we can assign to the algebra of the region. The integral, however, of A over any closed p-dimensional surface is an observable, and one can see this in the abelian case using Stroke's theorem, namely that the integral of A is the same as the integral of F over a open p+1 dimensional surface. Is this closed p-dimensional surface are non-contractible inside a region? This phi operator cannot be recovered from physical operators that belong to the algebra of the region, and therefore cannot be locally generated in the region. We will call them non-local operators. And the inclusion of these non-local operators in the algebra of a region is simply a choice. Let me be a little bit more specific. The smallest algebra one can assign to a region is what can be called the additive algebra, and it's essentially the algebra one obtains from gluing algebra of small balls inside a given region. Then to that algebra, we can add all possible non-local operators, none of them, some of them. The only important requirement is that causality is always valid. But if it's not saturated, these non-local operators produce Haag duality violations in these regions with non-trivial homotopy groups pi p. These arguments I did can be generalized also to non-abelian cases. It has been done by Horacio, Javier, Marina Huerta, and Diego Pontelo. But what I would like to focus today is in the equivalent classes of non-local operators. We can define these equivalent classes by taking some non-local operator inside some region of spacetime as the non-local representative times every local operator that appears in the algebra. What we have proven is that if we have a symmetry group that has an air current, then the non-local classes associated to any given region cannot be charged under the action of that symmetry. The proof is essentially an algebraic quantum field theory proof. It follows from studying twist operators that implements the symmetry locally with or without another current. And the going back statement, it's almost proven. We know that these twist operators exist and that they concatenate when one like to unite them from different regions, but we are missing the convergence to the another currents. This statement might seem a little bit obscure, but it's a little bit more clear if one uses to rederive Weinberg-Witten theorem. This can be done as in 3+1 dimensions. We know that theories of massless particles with spin equal or greater than 1 have emergence IR one-form symmetries. For instance, in the case of the Maxwell field, they are generated by the field strength F mu nu. This implies that global symmetries, not Poincaré, under which massless particles of spin equal or greater than 1 are charged, cannot be generated by another current. We also know that theories with massless particles of spin equal or greater than 3½ have these emergence IR one-form symmetries, but these create charges that carry Poincaré indices. This is the case, for instance, of the spin 2, the case of the graviton with the Riemann tensor. So if one applies these theorems, one obtains that theories with massless particles of spin equal or greater than 3½ cannot have a stress energy tensor. Also, some interesting facts about these non-local classes is that they always come in dual pairs assigned to complementary regions. This is a consequence of the von Neumann's double commutant theorem, and that these Haag duality violating classes assigned to both regions form a group under which the non-local operators of the complementary region are charged. This can be seen because any algebra one associated to a region has to close an algebra on itself. This statement is more clear in the case of the free Maxwell theory in phi+1 dimensions. We can see that we have two closed form fields. These are the field strengths and the dual field strength that can define the most general non-local operator as a dion, which is a product of a Toff loop and a Wilson loop, labeled by the charge of the Wilson loop and the magnetic charge of the Toff loops. And essentially can be thought as the product of the exponential of the fluxes. As the fluxes for complementary rings do not commute in the sense that they are proportionally to the linking number between the surfaces, one obtains that the dions associated to some spacetime regions with non-trivial homotopy group pi1 do not commute with the dions of the complementary region, and therefore these are charged under the first ones. That can be deduced from this formula here. And if one studies the fusion rules, one can further see that the group of non-local classes is R2 times R2. So going back to the previous case where we were talking about charged classes, if we see that these Haag duality violating classes are charged under the action of a continuous symmetry group, then the classes itself for both regions must form a continuum. This leaves us with two cases. The first one is the case where we have a non-compact p-form symmetry, in the sense that the Haag duality violations group is non-compact. We have proven that this implies that we are dealing with a QFT with a free massless sector, or that the theory needs to be UV completed with charges that break down all generalized symmetries that are non-compact to compact ones. This is essentially produced because in the case that the group is non-compact, it takes this form R times R, which involves a commutator between the non-local operators similar to these of the fluxes of the Maxwell field. And that commutator or the correlators that produce that commutator do not renormalize. The remaining case is the one of the continuous compact p-form symmetry. This can only happen for a p-form symmetries in spacetime dimensions 2p plus 2, but in principle should allow influencing theories that can be UV completed. This is the case of the ABC anomaly and the chiral symmetry, and it's essentially what I will talk about from the rest of the talk. I think the best setup to study this is the effective field theory of the neutral pion. We can describe the dynamics of the neutral pion by an action that includes a kinetic term for the pion field, a kinetic term for a Maxwell field, and a quasi-topological coupling that comes from the Wess-Zumino-Witten term. Essentially, this term secures that the pion equation of motion includes the ABC anomaly appearing at the classical level. Namely, if we define the current as the gradients of the pion field, then the conservation law of the current essentially encodes the anomaly. And as in the usual treatment of the ABC anomaly, we can rewrite this equation of motion as the conservation of a gauge-dependent chiral current, which is this one here, that produces this charge here. The thing is that one can check that this charge Q commutes with the stress energy tensor and implements the symmetry transformation over the action. as it essentially acts over the gauge-invariant phase space variables only by shifting the pion field like this, and leaves invariance the other canonical coordinates such as the magnetic field, the pion velocity, and the electric field. So in this case, we are dealing with an ordinary internal U1 symmetry that transforms any algebra of local operators for any region into itself. But the symmetry is not implemented by a well-defined other current, being this the only new feature that that's not generally found in other internal symmetries. This is indeed aligned with the previous theorem I was telling you about, with the idea that we might have to find charge classes. And indeed, in the pion theory, we find two forms. The first one is the dual of the field strengths, which is conserved only due to symmetry. And the other one is this G operator over here that is conserved due to the gauge field equation of motion, and involves a term with the field strengths and a second term that couples the pion field with the dual field strength. This allows us to define non-local operators in the theory, and the most general one is similar to the free Maxwell case, is the dion, labeled by the charges Q and G, like here, with the exponential of the fluxes, and obey fusion rules and commutation relations that produce a non-compact group of Haag duality violation that is R2 times R2. What is different in this case from the case of the Maxwell field is that because this G operator has this composite term here, one can see that it transforms under the action of the charge, or the unitaries one can define from the chiral charge. And therefore, this explains why there cannot be another current for this symmetry. The question that remains in this case is how is the symmetry implemented over algebras of trivial or also non-trivial regions? That has an answer that is given by Bushnell, Doplicher, and Longo from the 80s. And essentially it's a theorem that states that when we have a theory with a global symmetry group G that obeys the split property, and I will come back to this in a bit, we can always find twist operators that act as group transformation on the algebra of a given region R by conjugation, namely the twist operation by conjugation does the group action over operators inside the algebra of a region, and leave invariant the operators outside that algebra. The split property, that was the only requirement of this theorem, essentially can be stated that when we have two algebras, one for the region R and one for the complement, that originally commute, which is the causality requirement, there is a third algebra, this N, that contains the algebra of the region, and its commutants contains the algebra of the complementary region. And for this N, this algebra N, the Hilbert space can split or factorize. And essentially, the proof of the theorem follows from the definition of some standard twist that can be constructed in a general way using modular tools. But they can be heuristically interpreted as the group action acting over one half of this Hilbert space. At this point, I would like to make some observations. The first one is that the split property might seem a little bit obscure, but is valid with great generality in quantum field theory. It only requires that the degrees of freedoms do not increase too fast in the ultraviolets, namely that the theory what we are dealing with has no Hagerdon temperature and the time-slide action. Second, if there is more than one algebra for a given region of spacetime, there is a different split N, like this N here, for each choice, and therefore there are well-defined standard twists that implement the symmetry for each choice of algebra. The third observation is that there are other more tangible construction of twist operators in many cases. Although these standard twists are always guaranteed to exist, one can find simpler ones. For instance, by addressing the gauge dependent charge Q with some boundary terms. Going back to the example of the anomaly, now that we know that we have this chiral U1 symmetry and how it's implemented, one can see that the pion model is an effective field theory with a non-compact form symmetry. That implies, as we would like it to keep being interacting, that the UV completion has charges that break down all the Haag duality violating groups from RR to a compact group that is U1 times Sept. This can be achieved by the completion of the model inside QCD with charged massless quarks, or at lower energies by the appearance of charged pions. Once we include the charged pions, we know that the charge of the Wilson loops has to take values between 0 and some minimal charge Q0, and the values of the top loops, of the charge of the top loops, have to take value of 2 pi over Q0 times K with K some integer number. This is similar to the Dirac quantization condition. And in this case, the compatibility of the compact group of Wilson loops, namely the compact U1 here, with the non-trivial action of the chiral symmetry, that is this one here over the classes, essentially fixes the range of the parameter lambda defining the chiral transformations to take values between 0 and some lambda 0, that is some natural number times Q0 squared over 2 pi. Once we have done this and consider the pion compactification radius, which in this case, one can fix it to 2 pi times pi, the pion equation of motions shows that the coefficient of the IBG anomaly needs to be quantized. This was a known result, but here it arises only from purely group theoretical terms. The resulting equation for the anomaly is this one here, where this n is the same n appearing here and can be related to the minimal charge of the chiral symmetry, which in the case of the pion theory is 1, and then we can match by anomaly matching this anomaly to the one appearing QCD, and it's the same result. An important point I would like to make is that this discussion also can be done in massless QED. In that case, the calculations are a little bit harder, and one needs to include correction to the commutator coming from triangle diagrams. And the charge non-local operators under the action of the chiral symmetry are the top loops, and this is due to the presence of the Witten effects. Another important statement is this can also be generalized to non-trivial backgrounds, as the non-local quantum physics that characterize the theory remain unchanged when we go to some other non-trivial metrics. In this sense, there is no need to invoke a non-invertible symmetry, as has been mentioned in some recent literature. Well, to finish, I have some conclusions and a conjecture. The first one is that the existence of non-local classes that arise from the presence of generalized symmetries that are charged under the action of a symmetry group imply that there cannot be another current for such a symmetry. The second one is that theories with charged non-local operators have a continuum of classes, and if the Haag duality violating group is non-compact, we have a free massless sector that appears at all scales, or the theory needs to be completed with charges that break the non-compact symmetry to a compact one. And third, in relation to the ABJ anomaly, the chiral symmetry in the presence of the anomaly can be interpreted as a global U1 symmetry, and its only peculiarity is that it has the presence of charged non-local classes. And in particular, we can use this fact to obtain that because of the compactness of the symmetry, the anomaly coefficient gets quantized and fixed. And to end, we have a conjecture that is that if we are dealing with an effective model that has a continuous symmetry without an error current, but no Haag duality violating sectors are charged under the action of the symmetry, then the model does not have a UV completion. We have an example and an argument in favor of this. The example is the case of the pion effective field theory in 6 dimensions. It essentially works as the same as in 4 dimensions. We add the Wessumino-Witten generalized term that produces the anomaly in 6 dimensions. But although one can see that an individual top loop is charged under the action of the chiral symmetry, the chiral symmetry is not allowed to change the class of the top loop. It only adds an local operator to it. This is because now the Wilson loop and the top loop live in different codimension surfaces. One is codimension 2 and the other is codimension 4. But as we know, this model in 6 dimension does not have a proper UV completion. The second, which is the argument in favor of this conjecture, is that, I don't know if you remember when I told you before, but the going back of our theorem, like the fact that non-charged classes imply the existence of a current. We have proven that these twist operators that implement the symmetry locally concatenate. Namely, if I take 2 twist operators for different regions and glue them together, I get a twist operator for the union of the regions. But we have not been able to prove the convergence to a current. And in this sense, this should require this condition about the UV completion. Well,
Valentin,
and that's all I have to say. That's all.
Great. So there is time for some questions.